Okay, so we have to put together this Born-Haber cycle for formation of potassium sulfide. So that's what's going to be at the bottom. So this is K2S solid, which is what we're making, and we're making it from its elements. So we've got 2 moles of potassium here, sorry, just K, not K plus yet. And we've got sulfur. You're not expected to know what the form of sulfur is, although you probably know that it's a solid, so that will do. It actually exists as S8, but you wouldn't be expected to know that. So that's your overall change. So that's your delta H of formation, and that's minus 418 kilojoules per mole. And then we just start with the metal is the easiest way. So if we start with the potassium, what we've got to do is break up its metallic bonds. So we'll turn that into potassium gas, leave the sulfur alone. And that's atomization of potassium, which is plus 90 kilojoules per mole. But this is where you've got to be careful, because you're making 2 moles of gaseous potassium atoms. That's 2 times the enthalpy of atomization. So that's plus 90 times 2 is plus 180. And then we have to turn those atoms into positive ions. So we get 2K plus in the gas phase, plus 2 electrons plus our sulfur. So that's the first ionization of potassium, but again we're ionizing 2 moles, not just 1. So that's plus 420 times 2 is plus 840 kilojoules for that one. Okay, and now we're done with the potassium, that's ready to go. So now we can turn our attention to the sulfur, and again, first job is to atomize it. So we're going to turn it into 2K plus 2 electrons, and now gaseous sulfur. And this time there is only 1 mole of it, of sulfur atoms that we're making, so it's just 1 times the atomization energy, which is plus 238. And now this 2-step process, which you've seen before with oxygen, you get the same pattern with sulfur, is the electron affinity. So it's transferring those electrons and adding them onto the sulfur atom to make first S minus and then S2 minus. And again, you've seen before that the first electron affinity is exothermic because there's attraction between the sulfur atoms and the first extra electron, but then once you have S minus, there's repulsion between that and the second electron, so you have to actually put energy in to force them together. So if we look at those ones, we've got this first one is going to give you 2K plus gas plus 1 electron plus S minus in the gas phase, so that's the first electron affinity, which is minus 200. And then we transfer the second electron on as well, so 2K plus S2 minus in the gas phase. And now we've got both our ions ready to go, and that one, sorry, is second electron affinity. That's the one we don't know, so we'll just write that down as second electron affinity. And finally, when we bring the ions together and stick them together to form a solid, that's the big negative one, that's the lattice enthalpy, which is minus 2125. Okay, so that's the cycle. Be very careful when you've done it, just have a quick scan through, make sure you haven't left out any state symbols, because those will cost you marks heavily if you just miss them out. And then most of the examples you'll have done, you'll have been calculating the lattice enthalpy by putting together a pathway that corresponds to that. This one, you need a pathway that corresponds to this change. So starting from there and going up to there, that's the overall change. So you just put together a pathway that does the same thing. It starts at that point, so it's going to go up here, and then down, and down, and down, and down, and then it's going to come all the way back up again. And you can see the overall effect of that pathway is that it starts where this one starts, goes down and back up again, and finishes where that one ends. So the sum of the steps will add up to the second electron affinity. So we get that the second electron affinity is equal to, this one's going up the page, so that's positive, so plus 200, and then we're going down, 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 so minus 238, minus 840, minus 180, minus 418, and then we're going up here, so plus 2125. So make sure you write that out, and then you just look at the answer, which should come to plus 649 kilojoules per mole. Okay, so those, once you've practiced them, are actually easy, but you've got to make sure that you get the attention to detail right. Otherwise you can sort of lose lots of marks cheaply. And then the usual sort of follow-up question when you have one of those formation Born-Haber cycles is something about comparing lattice enthalpies, and that's what we've got here. So you're comparing these two. If you weren't familiar with rubidium, you've got to find it on your periodic table. Don't guess what it is, but you've got to find it, and you find it's in group 1 underneath potassium. So you can see that these are very similar compounds, and all you have to remember is that lattice enthalpies depend on two things. They depend on the charges on the ions, so the higher the charges, the stronger the attraction will be, so the more exothermic the lattice enthalpy, and they depend on the radii of the ions. The smaller they are, the more focused the charge is, again, the stronger the attraction will be. So for these, because oxide and sulfide are both 2- ions, then the charges are the same, and the difference is in the radius. So what you say is that O2- and S2- have the same charge, but, and obviously sulfur's lower down in the group, so it's got an extra shell of electrons, so O2- is smaller, which means that it will be more strongly attractive to positive ions. So the important thing about the way I've written that is that I used the symbols for oxide and sulfide. You can say the oxide ion and the sulfide ion in words if you want to, but what you can't say are things like oxygen is smaller than sulfur. It's got to be very clear what particular particles you're talking about, and the easiest way to do that is use the symbols for the ions. And again, make sure you don't say things like atomic radius, because we're talking about ions here. You can say ionic radius, but the simple thing, if you put the ions down, you can just say O2- is smaller than S2-, and then you avoid the problem. Okay, and the outcome of that is that, okay, we're going to be expecting so far rubidium oxide to have the more exothermic lattice enthalpy, because the oxide ion is more attractive than the sulfide ion. But then we come to the positive ions, and they're both 1+. So again, our comparison starts with the fact that Rb+ and K+ have the same charge. But then again, we just do the comparison of radii, and rubidium is going to be below potassium in the group, therefore the rubidium plus ion is going to be bigger. So you say, but Rb+ is bigger than K+, which means it's going to be less strongly attracted to negative ions. You can specify what, don't just say less attractive, because they'll say less attractive to what. So less strongly attracted to negative ions. And so then you see what the problem is, that based on the negative ions we'd say this one has stronger attraction, but based on the positive ions we'd say this one does. And so you can't tell. And so that's what you say, that you get opposing effects on the attraction and therefore on the lattice enthalpy. So there are lots of different variations on those questions. That's just, a slightly different one where you can't come to a clear conclusion. But the point is that it's always the same ideas, so if you've practiced a few of them, those questions should be relatively straightforward.